All right, we're going to talk about optimization problems here, and this will be the first example we do. This was assigned out of the textbook. This was question number 2. But first, optimization is basically finding maximum and minimums within some given context. So we're not just looking at some random equation, finding where its maximums and minimums are. We're looking for it in a specific context. It's important to note that the word optimization does not always mean finding maximums. Sometimes the minimum is the optimal circumstance. Talking about expenses or costs to produce an item or run a business, then obviously you want your cost to be minimum. If you're talking about profits in the same scenario, then you want that to be a maximum. So it's important whenever you look at a problem to identify what are we trying to optimize, and is the maximum or the minimum the optimum situation. So we got to remember, maximums and minimum values occur when our derivative is equal to 0, also when derivatives do not exist, and sometimes at endpoints of an interval. Sometimes you have functions that stop at a certain point, and that's a potential maximum or minimum. So we have some goals. The first thing we have to do is we have to write an equation. It's telling me I'm wrong here. There we go. An equation that describes the situation we're talking about. So we got to identify if we're talking about a profit or we're talking about a volume. Whatever we're talking about optimize, we've got to write an equation for that scenario. Sometimes we have to write a second equation. Sometimes our first equation has more than one variable, and we need to identify a second equation or a second equivalence that's given to us so that we can eliminate a variable. Now that's not an unfamiliar concept because we did that when we did related rate problems as well. We have to take the derivative of our equation. We've got to find the values that make our derivative equal to 0. And then we've got to determine if those values are maximums or minimums, and there's a variety of ways we can do that. So this problem out of the textbook, question number 2, an open top box of maximum volume is to be made from a square piece of material 24 inches on a side by cutting equal squares from the corners and turning or folding up the sides. So we've got a square piece of material, let's call it cardboard, and we're going to cut the corners out of it, some unknown amount, and then we're going to fold the sides up to create this now three-dimensional figure. Our starting length of this material is 24 inches, starting width is also 24 inches, and it starts off as a 0 height, meaning it doesn't have a volume at the start because it hasn't been folded up yet. Since we're folding it up an unknown amount, and we're going to do it on both sides, so here's our length, so we're going to take an x out of this side and x out of this side. Our length after we start folding this up is going to be 24 minus 2x, and that height can change, so it's a variable. The width was also 24, so it would also take away 2x's, 24 minus 2x. And the height of our box is now going to be this value of x. Remember, volume of a rectangular solid is length times width times height. So in our case, we have 24 minus 2x times 24 minus 2x times x, or a volume equation of x times 24 minus 2x squared. So they give us three parts here, A, B, and C. And part A says, analytically complete 6 rows of the table, such as the one below. First 2 rows are shown. So they're giving you the various heights. They're having you plug them into the length and width, and then they're going to have you use this volume equation to come up with a volume. Now I did that, but I cheated. I used Google Sheets. And I've copied my Google Sheet right here, and I've actually gone all the way up to 12. So we've got our height of our box, our x values. Our length was 24 minus 2x, and you can see I plugged all the different x values, or length and width, in there. And then I have written out the volume equation, x times 24 minus 2x squared, and I've done that with the numbers in every piece here. Then I've actually plugged the values in and calculated a numeric volume, and you will see that one of these, if you watch these, it starts at 0, bigger, 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 hits 1024, 980, it's smaller. 864, smaller, smaller, smaller. So our volume increased up to this 1024, and then it began to decrease. Hey, this is a great way to do them if every single math problem in the world always came out to a whole number solution. We know that that's just not the fact of the matter. So this is not a process that can work all the time, but it does give us a starting point. we have an idea that we should have a maximum volume between 3 and 5, because that's where we saw it increasing and then we saw it decreasing after that point. Question letter B says, write an equation for volume as a function of x. And we've already done that. This is what I read up above. Again, starting length, width, and height. What happens after we fold up the sides x dimension to the length, the width, and the height. And we've got a volume equation here of x times 24 minus 2x squared. So now they say find or use calculus to find the critical value for the volume and find the maximum value. So here we have this equation, v of x equals x times 24 minus 2x. Our goal, now that we have our equation, is to find the derivative of that equation. For most people, we could do a quick product rule with a chain rule on this. It's not really that difficult, but a lot of students in the past have always tried to multiply this out into a polynomial first. So we might as well go ahead and do that. V of x equals x parenthesis. And if we square this, we should get 24 squared is 576 minus 24 times 2 should give us 96x in the middle. And we're going to square this last term. It's going to give us a positive. 2x squared is going to give us 4x squared. And then we'll go ahead and distribute that and give us a volume equation. V of x is equal to 576x, distributing the x, minus 96x squared plus 4x cubed. And that gives us a very simple power rule here derivative. New equation, now v prime of x. 576x would give us 576 minus 192x when we use our power rule plus 12x squared, and that would be our derivative. Personally, for me, what I would do to this is I would reorder it. You got a positive 12x squared, so you could bump that out to the front. V prime, new equation, V prime of x equals 12x squared minus 192x, and we're putting it all in the exponent, minus 192x plus 576. And now our job is going to be to set this equal to 0 and solve this. So, new equation, 12x squared minus 192x plus 576 equals 0. Lots of ways you could do this. If you have a graphic calculator, it's probably the easiest way to graph it and see where it hits the axis. We could factor out a 12, which would be my method. 12 would leave me with x squared minus 16x plus 48 equals 0. And lastly, we're now going to have to factor this quadratic here in the middle, and that's going to give us 12. New equation, 12. Factors of 48 that are going to add up to negative 16, negative 4, and negative 12 would be the way to go. It's going to give me an x minus 4 and an x minus 12. Double check our math here. That's going to give me a negative 4x and a negative 12x, which would give me the negative 16 and would give me a positive 48. So we know that's the correct answer. So we found our derivative. We're setting it equal to 0 to find out where it equals 0. That's going to give us two solutions here. First, it's going to give us the solution. Remember, 12 constant. 12 will never equal 0. That's not going to give us a a critical value. X minus 4 equals 0, that's going to give us x equals 4 as a solution. And x minus 12 equals 0, that's going to give us x equals 12 as a solution. So we found two critical values for this, but I'll tell you what, this one's not going to work. And the reason x equals 12 is not going to work for us is because if we go back and think about this shape here, it was 24 inches by 24 inches. If you were going to fold one side up, if you're going to cut 12 inches out of one corner, 12 by 12 and 12 by 12 and 12 by 12 and 12 by 12, you're going to cut 12 inches out of each corner. You're not going to have any piece of cardboard or material left. Or if you think about it from folding standpoint, if you take this piece of paper and you fold one side up 12 inches and the other side up 12 inches, all you've done is fold your paper in half. You no longer will have a box and you won't have a volume. So the x equals 12 is not going to be a viable solution for us. In fact, if we look at my table here, you could see when I plugged in 12, I got a solution of 0. So we know that that's not a viable solution for us. So our answer is going to be x equals 4, which is reflected here when we saw this in the table. It did come out to a whole number in this case. Now, if we didn't have that, how would you know that x equals 4 was your solution? Well, the simple thing to do would be to plug a number smaller than 4 and a number bigger than 4 into your derivative. So if we think v, let's do this in an equation, v prime of number smaller than 4, let's go with 1. And if we plug that in, we plug in 1, we might as well plug it into here into the easiest form. 12 times 1 minus 4 is a negative number, and 1 minus 12 is a negative number. And when we do that, we're going to get a positive solution there, and that's important to us. Okay? When we plug a negative number in, or a number smaller than 4 into our derivative, we got a positive slope. Okay? So we know that when we have a positive slope, that means our function is increasing. New equation. V prime of, let's plug in a number bigger than 4, let's plug in 5 and see what happens. So when we plug 5 in, 5 minus 4 would give us a positive answer, positive 1. 5 minus 12 would give us a negative answer. And if we have a positive number times a negative number, that's going to give us a negative answer. And if we have a negative slope, that means our function is decreasing. So if we're increasing on values to the left of 4 and decreasing on values to the right of 4, that means we had to at some point hit a maximum value. So we know x equals 4 is going to be the correct solution. Now the problem does want us to go back and actually calculate the volume, which would simply mean going back to our volume equation and plugging 4 into it. So we can do that very easily. 2 times 4 is 8, and 24 minus 8 is 16. And 16 squared is 256, and 256 times 4 that we would plug in here would give us the 1024. So we know that that was the correct answer. Okay? So I hope that was helpful on how to solve a problem like this. I've also set up, and I will share this as well, this is a Desmos graph of our volume function, x times 24 minus 2x, and we can see that there actually is, did I graph it here? Yeah. If we look at x equals 4 and we draw a vertical line there, we'll see that at x equals 4 is where this hits the maximum. Now, I've graphed a lot of other things here too that we can match up. For instance, I graphed the derivative. So your blue graph is the derivative of your volume, and this is the key point right here. Our derivative, our blue graph, hits the x-axis at 4 at exactly the same point that our volume function has its maximum. And if we look over here, we'll see that this would actually be a minimum value as well. This is a low point in the graph, and that low point in the volume matches up with where our derivative also hits the x-axis and is 0. Now in this case, they both hit the axis at the same spot, That's not always going to be the case. Put a point here, and I made a little tangent line so you could actually take a look and see the slope as we take this point and drag it. Look at the slope values. It only will go back to 0. So we've got 0. We've got a slope of 576, but here's the key point. Positive numbers, positive numbers, positive slope, positive slope. When we get all the way up here to the top, our slope becomes 0. And after that point, what does our slope become? All negative values. So remember, slope is another word for derivative. When our slope is positive, our function is increasing. When our slope is negative, over here, our function is decreasing. And I've got this limited to 12 here, but if I was to open that up, let it go a little further, we'd see that when we get back down here to the bottom, it will become 0 again. And then as we start increasing, as our point starts going up the graph, notice our slopes became positive again. So that relationship between what the shape of your function, when is it going up and when is it decreasing, going down, is reflected in your derivative by whether or not you have a positive slope or a negative slope. And when that slope becomes 0, you know that you're either at a maximum point or a minimum point. So I will share the link to this as well, and I hope this was helpful.